Up until now, you've seen methods on both string and scanner that take strings that get interpreted as regular expression patterns. What does that mean? Well, the first thing that happens is the string containing the expression is passed to the compile method of a pattern class, which returns a pattern instance. This string, the regular expression, is said to be compiled into a pattern by Java's regular expression processor. This compilation process consists of first checking the string for syntactical correctness. Second, building an internal representation consisting of a decision tree made up of nodes and Boolean decision points derived from the various parts of the regular expression. And just as importantly, optimizing the pattern by simplifying the expression and eliminating redundancies. This process increases the efficiency of matching the expression to character sequences. By compiling regular expressions into pattern objects, you benefit from improved performance and code efficiency on subsequent matching. The compiled pattern can be reused across multiple matching operations, saving computational resources and reducing processing time. Let's jump back into some code and look at the pattern class a bit more closely. I've created a project called Pattern Matching and have the main class ready with its main method. The first thing I'll do is set up a string to test a few regular expressions on. I'll make a string variable named sentence and set that to the string literal I like motorcycles period. Next I'll call the static method matches on the pattern class. This method returns a Boolean, so I'll set up a Boolean variable called matched. I'll then call pattern.matches, and the first argument is the regular expression string. I'll use one similar to one from the mini challenges expressions, so it'll start with a capital letter followed by 0 or many characters and end with a single period. The second argument to the matches method is the string I want to match to this expression, so I'll pass sentence there. I'll print out if this matched and include the sentence in the output. I'll run this to review what we get. I'll get true, meaning this regular expression successfully matched the sentence I like motorcycles period. What if I want to test this on another sentence, like hello world for example? If I call this same method, the code will again compile the string into a pattern. If I were going to use this regular expression to check thousands or even millions of character sequences, using this method would be highly inefficient. Instead, I want to create a pattern from this expression, and I can do this by calling the compile method, another static method on pattern. I'll call this first pattern, assigning it the result of calling pattern.compile, passing it the same regular expression. I'll set up a local variable, and for now I'll just make var the type. I'll assign that first pattern dot. I'm going to pause here, allowing IntelliJ to show me the various methods I can call on this pattern instance. The first thing I want you to notice is that there isn't a method that's similar to the static method matches. I can't just call matches with a string here and use the compiled internal structure on this pattern instance. That doesn't seem immediately useful at first, but there is a method here called matcher that takes a char sequence. It returns an instance of a matcher class. When you compile a regular expression into a pattern instance, you'll need to use it with this matcher instance. In this case, I'll select this matcher method. I'll pass my sentence variable as the argument to the constructor. The type is matcher, returned by the matcher method, and the matcher class has a matches method on it, so I'll call that now. This method doesn't take any arguments, so I'll just call this within a println statement. I'll call matcher.matches and then include the sentence again. Let's review the output. I'll get the same result, that true came back from the matches method for this particular sentence, I like motorcycles period. In this case, I took 3 lines of code to do what I did in 2 on the lines above, to test whether the string matched this regular expression. You might be wondering, what's the advantage in that? If you're only testing the regular expression against an entire single sentence, there's probably not an advantage, but the matcher class does have several advantages over using the pattern class alone. In addition to matching on the entire input, matcher offers 2 other operations for partial matching. These methods are looking at and overloaded versions of the find method. Matcher supports capturing groups and granting access to the text within the group, which I haven't yet covered, but which I will shortly. Matcher can be reused for multiple match operations on different string inputs, meaning the pattern doesn't have to be recompiled. There are some disadvantages to using matcher though. An instance of a matcher class has state, which changes as operations are performed on it. This means the matcher class is not thread safe. It also means state may need to be reset before a new string is evaluated. Getting back to the code, I'll first print out the sentence length. Next, I'll print the match's ending index by calling the endAccessor method, which gets set after a match has been made. Let's review the output again. You can see that after matching, the ending index is equal to the string length, meaning the entire string was consumed in the match. Next, I'll use the LookingAt method. I'll call this from within a println statement. This method also returns a boolean, and I'll print the sentence out again. I'll copy the matched ending index println statement and paste a copy at the end of the main method. If I run this code, you can see that I get the exact same results from both of these methods, matches and LookingAt. The search in both cases used all the characters in the entire string. There is a difference though. The LookingAt method will always start at the beginning of the string, but will stop matching, returning true, even before it finds the end of the string. In other words, this method doesn't have to match the entire string. I'll change my sentence, updating it to say, I like BMW motorcycles, and make that contain periods. If I run the code now, I still see that I get the same result from both calls, matches and LookingAt. Did you expect the LookingAt method to return just the part of the sentence that said, I like B period? That's a pretty good guess, but you can see that's not what happened here. That's because the expression which uses the dot asterisk is what's called a greedy regular expression. Greedy regular expressions match as many characters as possible. The expression period asterisk, which is a greedy expression, matches any number of characters including the empty string. Reluctant regular expressions, on the other hand, match as few characters as possible from the input text. The regular expression period asterisk question mark matches any number of characters, but stops at the earliest successful point, where the overall pattern is matched. The default type of regular expression is greedy. You can use the question mark to be a quantifier modifier, making the regular expression reluctant. This will make more sense when you see this in code. I'll change first pattern, adding a question mark after the asterisk, which sets up a reluctant expression. Now if I run this code, notice that the result from the matches call is the same, both return true, but look at the matched ending index after the LookingAt method, it's 9 and not 26. This means the LookingAt method call matched this reluctant regular expression in the first 9 characters. I can use this endAccessor method to print out the exact string that matched the pattern. I'll print matched on, then I'll use substring on sentence. I'll start with 0 and end using the result of the matcher.end method. I'll run this to see what we get. You can see matched on and I like B period is the result. This was the least number of characters for this regular expression to be true. Maybe now you're wondering, why didn't the matches method do the same thing since I passed it a reluctant regular expression? As it turns out, the matches method requires that the whole string matches, so it doesn't honour the request to use only the least number of characters in this match. It will always use every character in the string to determine a match. Let's look at another matching method called find. To show you this one, I'll copy the last 4 lines and paste it below. I'll change the LookingAt method to the find method. If I run this code as is, I get true back from the find method, but my matched ending index is 11. This output isn't quite right because I didn't actually match that substring shown there. To get the actual match, I need to change this last statement, which is currently using 0 as the starting index. Instead, I should use matcher.start, which is where the find method started searching. Let me do that and let's see what we get. Running this now. I can see my regular expression really matched on just the M period part of the sentence. The find method picks up where the LookingAt method left off. If I want to start from the beginning, I'll need to reset this matcher instance, and I can do this simply by calling a noargs reset method on matcher. I'll insert this just above the find method printout. Running the code with this change, I'll now get the same result as calling the LookingAt method above. I didn't have to call reset between the matches and LookingAt methods. These methods don't set an incremental state that'll be used in their execution. Whenever I call either of these methods, they'll always use a starting index of 0. But the find method uses the ending index of the matcher instance as its start to the next match. This will become clearer in the next video when I use the find method in a loop to print all the reluctant matches in this string. See you in that next video.